Kia ora everyone, welcome to level 3 physics, first level 3 physics video I've done because I've just recently learned the standard. So let's jump into it. The first question. Part of this track for a toy cart set is a horizontal banked curve and part of it has a vertical loop. Now they've not shown us the photo, so apologies for that. Because for some reason NZQA always blocks out the photos, which sucks a bit. Toy cart has mass of 0.12. On the diagram below it, draw a vector diagram, identify the net force that is responsible for the car going in a horizontal circle around the bank curve. Label the net force. So, the car has a weight force downwards equal to its mass times gravity, and it will have a reaction force at 90 degrees to the track. Now, this reaction force can be split into two components. Ignore the not very straight lines. The vertical component is equal to mg because the car is not moving vertically, and the angle of the banking is theta degrees, and this angle here is also theta degrees. And to use some trigonometry, this horizontal component is mg tan theta. So, this is all going to be quite useful soon, but you'll see the net force comes here. It's this component here, and this is the centripetal force that acts towards the center of the circle, which causes circular motion, like this. So I guess you'd label this force, label the net force. Net force, inwards. Yep, there we go. I mean, that's net, it's a pretty vector diagram, if I'm honest. But whatever. The banked curve of the car track has a radius of 0.75 meters. The angle of the banking, if it goes around the bank curve at 1.55 meters per second. Okay, so what you have to identify here is that this horizontal component is equal to the centripetal force that causes the car to go around the circle. So what we're saying is mg tangent of theta, this horizontal component, is equal to the centripetal force, mv squared over r. Now, we want to know the angle of the banking, so I'm going to rearrange this for tan theta. Tan theta equals mv squared divided by mgr. The m's cancel, and you're left with v squared on gr. So, putting in the numbers, velocity squared, 1.55 squared, taking gravity is 9.81, and the radius is 0.75. Tangent of theta is equal to 1.55 squared divided by 9.81 times 0.75, 0.326, and then if you take the inverse tangent of that, making sure your calculator is in degrees, tan inverse of 0.326 is 18 degrees. Yep, 18 degrees. So the key thing with this question is just to understand that on the banked curves, this horizontal component is the centripetal force. This is where this equation here comes from. And that is, if you don't recognize that, this question is impossible, essentially. This is a very useful equation to remember for mechanics. It comes up in lots of circular motion questions. Vertical circular loop that makes up part of the car track. Explain why the person sitting in the car, the actual car would feel heavier at the bottom of the loop compared to the top of the loop. Begin your answer by drawing labeled vector diagrams at the bottom of the opposite page to represent the forces acting on the car. When it's the top of the loop and when it's the bottom of the loop. Okay. Firstly, the weight force downwards, mg. It's the same. It doesn't change. The car doesn't get heavier. the gravity doesn't change. Gravity doesn't change. However, the reaction force at the bottom, I'll call this force reaction, is bigger than the weight force at the bottom. And the reason for that is because the excess of the reaction force is the centripetal force, which provides the circular motion. Remember, you have to have that force to the center of the circle. So the reaction force is greater than the weight force at the bottom, and the reaction force is 0, essentially. Well, it doesn't have to be 0, but it's less than the gravity force. You'll see this little arrow here. If the car is going at the minimum speed possible, it's 0, but it doesn't say it is, so you would just put a smaller arrow. The reaction force is less than the weight force at the top, and it's greater than the weight force at the bottom. And so that means at the bottom, you feel a greater pull or reaction upwards than you would at the top. And you can imagine this. Imagine yourself spinning in a vertical circle, or spinning a bucket in a vertical circle. If you spin it at the speed just enough that it spins around, like a bucket on a piece of string. Here's my bucket on a piece of string. When it gets to the top, you get that sense that the bucket doesn't weigh anything. And that's because there's no reaction force. The centripetal force is just the weight force downwards. And that's why it feels weightless. Would feel heavier, so beginning answer with drawing labelled. Okay, so now we've got to put all that into words. So, marking schedule, yeah, so at the bottom of the loop, the reaction force is greater than the weight force downward. This is because the reaction force supplies the centripetal force to maintain circular motion. Okay, that's a key point. Do they not even provide this? Yeah, provide the centripetal force. They've really shorthanded it. Okay, so and then always comparing contrast at the top of the loop, the reaction force is less than the weight force, as both are acting in the same direction to supply a centripetal force. Since the reaction force is bigger at the bottom, people feel heavier. You're not actually heavier, you just feel heavier. I guess weight. Yeah, I wouldn't use you are heavier, I guess the toy car of mass approaches the vertical circular loop. This is a difficult question. It's probably one of the harder questions you'll ever see. You know, you could almost see this turning up in a scholarship paper, although maybe they probably wouldn't give you actual numbers. It'd just be figures like mass m and radius r. Carry the speed with which the car must approach the bottom of the loop to be able to go around the vertical circular loop, such that the car seems weightless at the top. So, what do we know? We know that the car feels weightless at the top, therefore there's no reaction force at the top. Which means the centripetal force, I'll say Fc at the top, is the weight force. If you say the centripetal force at the top is equal to the weight force, you're not wrong, but it doesn't show great understanding, because the centripetal force it's always a different force. It's always the weight force or the reaction force or the whatever force. It's not really its own thing. So at the top it is the weight force. It's not equal to the weight force. It is the weight force. Of course, this is going to get contrasted by the fact that the very next line of working is mv squared over r at the top is equal to mg, which implies that v squared is equal to gr, which implies that v is equal to the square root of gr. So this is the velocity that you have to go at the top of the circle, such that the centripetal force is equal to the weight force and there's no reaction force. So velocity equals, putting in the numbers, we know gravity, we know the radius, so we'll take square root of 9.81 times 0.25, and you're left with 1.566 meters per second. Now, this is useful because it gives us speed at the top, but we want to know the speed of the car at the bottom of the loop. And to do that, you have to consider energy. So I'm gonna say, suppose the energy of the system does not change as the car goes around, assuming there's no friction or whatever. The energy of the system is the same, which means the energy at the top is equal to the kinetic energy, half mv squared, plus the gravitational potential energy, assuming this is on the ground, right? Plus mgh. Now we know the velocity at the top. It's 1.566. That's what we've deduced based on the fact that the car is weightless at the top. And we know the mass of the car, we know gravity, and we know the height of the track. It's twice the radius, 0.5. And so if you put in the numbers, you go half. The mass of the car is 0.12. The velocity at the top is 1.566 squared, plus the mass is 0.12. Gravity is 9.81, and the height is 0.5, and you'll end up with 0.7357 joules. This is the energy of the system. It is the total energy of the system. No matter where the car is, the sum of its gravitational potential energy plus its kinetic energy is 0.7357. Now that's very useful because now for any point on the circle, you can work out what the velocity is based on the sum of its energies. At the bottom, there is zero gravitational potential energy. Okay? Which means energy at the bottom, it still has to equal 0.7357. That's a fact. But it is equal to half times the mass times the velocity of the car at the bottom squared, plus 0, because there's no gravitational potential energy. So now it's just a simple rearranging. You get 2 times 0.357 divided by m square rooted is equal to velocity. I've just rearranged the energy kinetic formula. You have half mv squared equals e. You can say v is equal to the square root of 2e on m. If rearranged, you multiply by 2 and then you divide by m and then you square root it. So that's just what I've done over here. And plugging in the numbers, we know the mass of the car, I won't bother rewriting it. 2 times 0.7357 divided by the mass of the car, which is 0.12, and taking the square root of that, we are left with 3.5 meters per second. So, I'll just check that's right. Yep, 3.5 meters per second. This question is tricky. It's obviously tricky, but you have to consider that for vertical circular motion, the energy of the system is the same always, unless you lose it to heat or sound or whatever. In real life, of course, in real life the car would spin around and it would stop, right? It would just come back down. It wouldn't keep going around in a circle because it would lose energy, and if it loses energy, it loses velocity, and it loses the car in real life loses velocity because it loses it to friction or whatever, slows down, it lowers its velocity, and because it lowers its velocity and its kinetic energy, it doesn't have enough speed to supply the required centripetal force, so it can't go in a circle, and then it will just fall down or whatever, which is very interesting. So 3.5 meters per second, you get that, you get everything else as well, you get E8. But yeah, so the energy in vertical circular motion is a very important concept to consider. I know I'm sticking on this, but it's so important. So watch that again if you're just a little bit stuck. Anyway, moving on. Question 2. We spent a bit of 15 minutes on question 1. Tane works weekends unloading barrels. Another energy question. In one instance, he rolls an empty barrel of mass 5.5 kgs and radius 0.28 on a ramp that is 1.34 meters high. The linear speed of the barrel when it reaches the bottom of the ramp is 3.4 meters per second. Describe the energy changes that take place as the barrel rolls down the ramp. So what you would say is gravitational potential energy is converted to kinetic energy. That's what they should say. Both linear and rotational kinetic energy to kinetic energy, both linear and it's actually quite important. So when things roll, they have translational speed. You know, like a soccer ball goes across a field, has linear kinetic energy, but because it's spinning, it also has rotational kinetic energy. Right. Calculate the rotational inertia of the barrel. And so they give us a few steps of how to do this, and they give us quite a bit of room. The gravitational potential energy at the top. So the total energy of the system is equal to the gravitational potential energy at the top, which is mgh. Okay, we know the height of the ramp, we know gravity, and we know the mass of the barrel. So m is 5.5, g is 9.81, height is 1.34. Put the numbers in, you're going to get 72.3 joules. That's the total energy of the system. The angular velocity of the barrel as it reaches the bottom of the ramp. The linear speed of the barrel when it reaches the bottom of the ramp is 3.4 meters per second. So if you look at your formula sheet, you're going to get velocity is equal to radius times angular speed. So, that is right. You'll see whenever you convert from, because velocity and angular velocity, obviously, they're the same thing, just in linear and rotational motion. And so, like, d is equal to r theta, acceleration is equal to r alpha. So v is equal to rw, it should be in here. V equals rw, yep. Which means that w equals v over r. Now at the bottom, it's going 3.4 meters per second linearly. So therefore, we can say w is equal to 3.4 divided by the radius, which we're given, 0.28. 3.4 divided by 0.28, and we get 12.14. Okay, so what do we have? What do we know? We know the speed of the barrel at the bottom, and we know how fast it's rolling. And so there should be enough information for us to work out what the rotational inertia is. Remember, rotational inertia is a measure of how difficult something is to roll. And so we have information. We know a bunch of stuff. So what do we know? The total energy of the system is 72.3 joules. Here it is, 72.3 joules. And at the bottom, there is no... Here's the barrel at the bottom. There is no gravitational potential energy. Assuming this is on the ground or whatever. You made that assumption. Which means that the 72.3 joules is equal, it's 4.7, there we go, is equal to linear kinetic energy, half mv squared, plus rotational kinetic energy, which is half iw squared. Now, we actually know all these variables except for I. So what I'm going to do is multiply everything by 2, 72.3 times 2. I get 144.6 equals mv squared plus IW squared. And I'm then going to say, well, 144.6 minus MV squared divided by W squared is equal to I. Now, how else can you do this? You could calculate angular momentum. Maybe they do it that way. They do angular momentum? No. But this is the expression, and so now we just put our numbers. 144.6, which came from multiplying the equation by 2 to get rid of these fractions, minus mv squared, so I subtracted it over to this side. So the mass of the barrel is 5.5. The speed of the barrel at the bottom, we worked that out, we're given that, is 3.4. Let me square that. Okay. And then we divide everything by W squared, which was, that should be radians per second, 12.14 squared. And you'll get 0.549. 549. Ah, yeah, there it is. Got like a meter squared here. The way they did it, they calculated each piece. Energy kinetic gained and lost and put together, but this is just the quick way of doing it, I guess. Just finding the equation. Once you have this piece here, you know the mass, you know the velocity at the bottom, you know the angular velocity at the bottom. All you've got to do is rearrange the equation to get I, and there you go. And here it is, except 0 point using unrounded values because we didn't calculate each step intermediately, we just did them at once. It seems the way they've worded this is maybe you have to show. Do you have to show each piece? I'd say no. This should be fine. You know, we did the 2 bits they wanted us to, so that's alright. That's alright. Holding a full bottle, you notice that when he holds the bottle with his arms outstretched, it's composed to substance of body. I don't know why it says he tends to spin more slowly. He does spin more slowly, would be a better way of putting it. So, Tane, sitting on a swiveling stool, holding a full bottle of water in each hand, he notices that when he holds the bottle with arms outstretched, he tends to spin more slowly. Okay. The angular momentum of this system is constant as no outside torque is acting on it. When Tane outstretches his hands, he redistributes the mass of the system further away from the axis of rotation. By doing this, he increases his rotational inertia. Because L is equal to IW, that's your angular momentum, a decrease to I means, a increase to I means a decrease to W. And in that final sentence, therefore, he spins slower with his arms outstretched. Do we know Tane's rotational inertia? No, we don't. Tane spins with an angular velocity when he brings. No, that's alright. We don't need to. Okay, so remember, angular acceleration is equal to a change in angular velocity divided by the period over which it changed, which makes logical sense. So the change in velocity is the final velocity, which is 7, minus the initial velocity, which is 3. We did this in 4.5 seconds. So that's 4 divided by 4.5, and that will give you 0.888888 on forever, so 0.89 radians per second. Now, you're going to have to bust out the, if you know calculus, you could very easily work out the number of revolutions, but you have to bust out the formula sheet, and it'll tell you that theta, no, I don't actually have the formula sheet, that's annoying. Distance travelled, I think it's equal to, oh well, I'll get a resource booklet. Resource booklet, level 3 physics. And there we go. Here it is. The angle at which you rotate through is equal to the average speed multiplied by time. That makes sense. So your average speed is your final speed plus your initial speed divided by 2. And the time over which we did that was 4.5. So that is 5 times 4.5, 22.5 radians. Now, we need the number of revolutions. So if you remember that one revolution is 2 pi radians, then the number of revolutions we want is equal to 22.5 radians divided by 2 pi. And that'll be 22.5 divided by 2 pi. Oh, fuck's sake. Divided by 2 pi. Calculator's broken. Right. 3.58. 3.58 revs. Bingo! Wait, how do they do it? 7 equals... Yep. 0.89. Could do it that way. That works too. Yeah, it all works. Cool. 3.58. Okay. So, when do you get E? That was E? Okay, that's probably the world's easiest excellence question, if I'm honest. I think this one should have been with E. That was also with E. Okay, cool. Simple harmonic motion. The spring has a spring constant of 24.6 newtons per meter. Simple harmonic motion. Given the equation relating simple harmonic motion as acceleration equals negative rotational angular velocity squared y, describe how the gradient of the line relates to the frequency of oscillation. So, the gradient is negative w squared. So if you've ever learned linear graphs, you should have done in like year 10 or year 11. Whenever you have a variable equals some scalar times another variable, you'll always get a linear relationship, whether it's like this, like this, like this. In this case, there's no shift, so it's going to go to the origin. Now, frequency. You'll notice that W equals 2 pi F. It's on the formula sheet, which means F equals W on 2 pi, which means that, actually no, hang on, W squared therefore equals 4 pi squared F squared, so this is equal to negative 4 pi squared F squared. And so you could say something like the gradient of the line is negative 4 pi squared F squared, relates to the frequency. By calculating the gradient of the graph, okay, so now you actually get to look at the graph. We know that the gradient, we'll call it M. No, we won't call it M. We'll call it negative W squared, is equal to a change in Y over a change in X. Change in Y, change in X. If we go from 0.02 to minus 20, for example, the Y change is minus 20. and the exchange is 0.02. And putting those numbers in, we get minus 1,000. So that means that W squared equals 1,000 equals 4 pi squared F squared, which means that 250 on pi squared is equal to F squared, which means that frequency is equal to the square root of 250 divided by the square root, divided by pi. Frequency is equal to 5.03 hertz, or per second, or whatever. So this is a look at the graph one. You calculate the gradient, and then you set the gradient equal to the scalar, and then we use the relationship we derived over here. And that means that t equals 1 on f, which equals 1 on 5.03, which does indeed equal 0.199. And you can see that because this is very close to 0.2, which is a fifth, and this is very close to a fifth. So there we go. Tana then pulls the spring of period t equals 0 down through a distance of 0.1 meters in equilibrium position. Okay, I'm not going to use the reference circle. I know a lot of teachers will always teach reference circle methods, but I'm not going to do that. I'm going to consider, here is the spring, okay? This is the equilibrium position in the middle. There we go. Now, the amplitude is 0.14. The period is 0.19. Now, they do give us the spring constant, 24.6. I'm going to write that over here, because it's probably going to be useful. Down to a distance of 0.1 meters. Shall we get to the next question? Oh, wait, hang on. Do we have to calculate the mass? Oh, whoops. I was wondering, because I was like, this must be useful for something. The mass of the toy, I forgot to read that. You know that t is equal to 2 pi the square root of m over k. Now you're given k, it's 24.6. So if you rearrange this, you're going to get m equals t on 2 pi squared times k, and then when you plug in your numbers, you get 0.0246. So you put this in for t, 2 pi is 2 pi, you square it and you multiply it by 24.6. So that's rearranging this formula, and that's how you get that figure. Okay, now this question. The reason that they teach reference circles is because there is a deep-nated similarity between simple harmonic motion and trigonometry. Namely, I can draw a graph like this. I'll say this is time equals 0, and this is time equals 0.199. If we start, the toy starts down here, and you imagine as soon as you let it go, it's going to spring upwards, and then it's going to come back down and spring downwards. And its velocity and its acceleration and its displacement are always changing. So it starts 0.14 meters, 0.14, this can be negative 0.14. This is time equals 0, time equals 0.199. At the first instance, let's say this is equilibrium here. Straight away, it is 0.14 meters away, and it moves. Oh, this is a graph of displacement from equilibrium against time, and it's going to look like this. It's going to be a sine wave, and so you'll notice that after half a period, so about 0.1 seconds, the toy is 0.14 meters away, but it's on the other side. It's over here. It's bounced all the way up and it's up here, and then it comes back again. Now, how do you find an equation for this graph? The equation for displacement is equal to the amplitude, 0.14. Now, this is a cosine graph. So, cosine. The reason it's cosine is because it starts at its max amplitude. If it was sine, it would look like this. Okay? Cosine, 2 pi divided by the period, which is 0.199. This is also angular velocity of a phasor, but if you've learned phasors, then you might know what that means. If you haven't learned phasors, then you won't. Multiplied by the time it's been spinning. This is an equation. The distance that the toy is away from equilibrium is equal to this at any given time. If you're doing level 3 calculus, you may have done the internal, trigonometry internal, and you'll see what's going on here. But by using this method, what this enables you to do is calculate the time it will take for the toy on the spring to travel a distance of 0.14 meters up from its release position. We want to go 0.14. Oh no, sorry, that's not the amplitude. The amplitude is 0.1. 0.1. I've made a mistake there. 0.1. That's the amplitude. What we want to do is we want to go 0.14 meters. And so we've passed equilibrium position, and we're going towards the other end. So we're going to be around about here, if that makes sense. So we need to work out the time it takes to get to here. This is at some time x. And so what do we know? We know that displacement is 0.14 minus 0.1, which equals 0.04. That is the distance we are away from equilibrium. So 0.04 equals 0.1 cosine 2 pi 0.19t, which means that actually just use a graphics calculator at this point. In fact, grab your graphics calculator out. I know this is taking a while, but it's important. Grab your graphics calculator out, take your graphics calculator for the exam. 0.1, put in the graph 0.1 cosine of 2 pi x divided by 0.199. And make sure your calculator is in degrees. Not degrees, in radians. And set your view window so that you are going from 0 to 0.2. And your y needs to go from negative 0.1 to 0.1. And it'll trace a cosine graph. And now you've got to go back to graph and you put a line at negative 0.04. And it'll trace a line through the graph for you. Now you go G-solve and intersections, and it'll tell you that this point here is at time equals 0.06278 seconds. And so that's how long it took for the toy to reach there. Now I would definitely advise watching this again and really just trying to understand what's going on. The fact that this toy bouncing up and down can be modeled by this curve. It's the same curve that models the tides of the ocean, for example. So 0.06278, they'll want that to a few significant figures, so say 0.063 seconds. 0.0628, there we go. Now, obviously they've got their phasor, and they've got, you see a whole bunch of numbers. You can learn to do it this way, your teacher will teach you this way. Accept other solutions methods that are reasonable. This is the other solution / method. They acknowledge that you can take level 3 calc and they'll teach you this method. This is the way I would do it. The phasor circles can be tricky and you mess up. This one, you literally just take your graphics calculator and, you know, it's the end. It's pretty easy. But it takes practice. Knowing you've got to get this equation. Once you can get the equation, then it's very easy to find the time just by taking your graphics calculator and putting a straight line through. Anyway, that's level 3 mechanics. With a bit of luck, we'll walk out of this exam. Oh no, there's more. Never mind, there's more. Tangi notices that once she's pulled down and set it oscillating synchronizing for the period of it, the amplitude gradually decreases with time and eventually this pin stops oscillating. This is called dampening, and it's the fact that in real life energy is lost. So if you imagine, if you put a little pendulum into oscillation, it eventually stops because it loses energy. So it's going to start 0.1 meters away from equilibrium. This is equilibrium. It starts here, and after one period, this is 1 period, this is 2 periods, this is 3 periods. After 1 period, it will have oscillated, but it won't be back quite as high. It'll be about there. It's lost some energy, and therefore it can't reach its max amplitude. Let me go again. Loses some more energy. Then it loses a bit more energy. Like that. Now, I've not drawn this great because, in theory, it should look fairly symmetrical about this line. But, oh well. All they want to show is that the period is the same. The period doesn't change, but the maximum amplitude with each cycle decreases, and you can see that happening on the bottom as well. That's what they're looking for. So you have to have time down here, your 3 periods, units and values. Okay, well, put in 0.199, 0.398, 0.597 in for your 3 time values. Now you don't actually know what heights it reaches. It depends on how much energy it loses. So this is what they want. Here it is, 0.1, negative 0.1, t, 2t, 3t. They've done it. See, their cosine graph it's a negative cosine graph. You can do it either way around depending on which side you take to be positive. Doesn't really matter. So anyway, damping, energy loss of surroundings, 3 cycles. Explain what causes this. So loss of energy. There's loss of energy which causes dampening, which causes the max amplitude to decrease, and eventually over time it stops oscillating, it just sits still. And so this is obviously, if you know how to do this, then you should know up here that it's going to be a trigonometric shape. Anyway, that's level 3 mechanics. The end. You get your E24, pat on the back. Well done.